Before we can start talking about periodic trends or the trends that you find on your periodic table, there's a couple background vocab stuff that we have to understand before that makes sense to you how the trends work. So there's valence electrons, effective nuclear charge, and electron shielding. First, our valence electrons are just the electrons in the outermost shell. The reason noble gases are so stable is because their outermost electron shell is full. It has 8 valence electrons. Those ions gain or lose electrons to be more like the noble gases. They want to be like those noble gases. And they might lose a few electrons, like the ones in the S block, or they to get down to 8 valence electrons, or they gain a few electrons to fill their shell, like your P block elements. The number of valence electrons for an atom is equal to the number of electrons in the outermost energy level. So remember, an atom is neutral, so it's not an ion. So the number of valence electrons for your atom is equal to the number of electrons in its outermost energy level. All elements in the same group have the same number of valence electrons. The number of valence electrons is equal to the A group number on the periodic table. So if you go by the American numbering, remember that's the third one down on your periodic table, the number of valence electrons is going to be equal to that group number on your periodic table. So here's an example, 3A. They have 3 valence electrons. Carbon would have 4 valence electrons. Nitrogen, phosphorus, arsenic would have 5, 6, 7, 8. So remember, 8 is where they have the full valence, full outer shell, full valence electrons. So all of your noble gases over here, 8 valence electrons, full outer shell. The reason like fluorine tends to have a -1 charge is because it's going to gain 1 more electron, and then it's at 8, so it's at its full outer shell. So that's the reason. The reason behind their charges is because they're trying to be like these noble gases. They're trying to get 8 in their outermost shell. Same thing with oxygen is usually a -2. 6, add 2 extra electrons, 1, 2. Now you have 8 in your valence shell. Your valence electrons will be 8. So that is the reason why they have the charges they do, and also an example of what valence electrons are. Here's a couple more examples of valence electrons and how you can find it. The electron configuration for boron is 1s2, 2s2, 2p1. The outer energy level is 2. So if you're finding the valence electrons from your electron configuration, you look for the highest principal energy level. And if you remember, your principal energy level are those big numbers in front. So in this case, it's 1, 2, 2. Those are my principal energy levels. I figure out which of these numbers is the biggest. In this case, it's 2 is bigger than 1. So my outer energy level is 2, the second energy level. And then I add up all of the electrons. Remember, those are my superscripts, the little numbers behind. So I have 2, 2, 1 here. The little numbers up behind, I add up all of those electrons in the outermost energy level. So I add up the 2s energy level, the 2s sublevel, and the 2p sublevel, and add up their electrons. And here I have 1, 2, 3. So I'd have 3 valence electrons for boron. A faster way to do it, I can also look at boron. It's in group 13, and the American number is 3A. So that means I have 3 valence electrons for boron. If I wanted to look at bromine, bromine's electron configuration, the abbreviated version is argon 4s2, 3d10, 4p5. I look for the highest energy level, 4, 3, 4. The highest of those is 4. So I'm going to add up all of my electrons in that 4th energy level. I have 2 here and 5 here in my 4p. 5 from my 4p plus 2 from my 4s gives me 7. So I have 7 total valence electrons. The highest energy level is just the biggest big number, the 4th energy level. Then you count how many electrons, your superscripts, are in all of those all of those number systems that start with the 4, that principal energy level 4. Make sure you don't forget to, it's not always going to be just the last one, and it's also might be skipping over. We have our 3D in between. So you always just find those biggest numbers. There's a 4 here, a 4 here. I add up the electrons in there, 2 plus 5, 7 valence electrons. Again, the other way you can do it is you can find bromine on your periodic table. It's in group 7A, so 7 tells you that's how many valence electrons it has. So you can look at the electron configuration, count all the electrons in the highest principal energy level, which is the big number in your electron configuration, not the superscript. Another option to find the valence electrons is just to look at the group number using the American numberings, the ones with the A's behind them, and then whatever group number it is tells you how many valence electrons the element has. So either way is fine there. Our next term is Coulombic attraction. The force of attraction between positive and negative. So remember, opposites attract. So for example, between our protons and electrons. So remember, protons are positive and electrons are negative. The Coulombic attraction depends on the sign of the charge and the distance between charges. So there is an attractive force between protons and electrons. So opposites are attracting. Those protons in the nucleus are trying to pull the electrons closer to them. But at the same time, we have a repulsive force between the two protons or two electrons. So two electrons, electrons closer in towards the nucleus are going to be pushing away the electrons further out. So remember, opposites attract, so the protons and electrons are going to be trying to pull together, but we also have the electrons in between there forcing those out, which leads to electron shielding, which is our next term. That's just because the attractive force between the nucleus, which is positive, and the outer electrons, which are negative, they are wanting to be closer together. But the electrons between them on those inside shields, on those inside energy levels, they push those other electrons away. So they're repelling them at the same time that the nucleus is trying to pull them in. You'll understand this a little bit more and the Coulombic attraction in the POGIL packet, but just so you have an idea, the electron shielding, we have our nucleus that really wants to pull in those outside electrons, but all the electrons that are closer are kind of fighting them off and beating them off from getting to be pulled in towards that positively charged nucleus. Next, we have effective nuclear charge. It's the charge felt by the valence electrons after taking into account the shielding. So we have our electron shielding that's taking place. So after we take into account our electron shielding, by looking at the average number of electrons between the nucleus and the electron that we're looking at, so we count how many electrons are between it. So it's kind of like how many girls are in line to get tickets to the concert. If there's a bunch of girls in line to get tickets to the concert before you, in front of you, you have a less likelihood of getting into that concert. So if you have that case, you have a less charge that's going to be pulled on you because there isn't those electrons between the nucleus, which is positive, and the outside electrons. The electrons between there are going to be pushing those outside electrons out. So electrons outside have little effect on the ones between. So if it's an electron, if you can look at this diagram, if our electron of interest is right here, electrons on the outside don't have any effect on the effective nuclear charge, but just the electrons between the one of interest, our electron of interest, and our positively charged nucleus, those ones have an effect, so they cancel out some of the positive because they're pushing away that negatively charged electron away from the positive nucleus. Here's a video that you'll want to go watch at some point to get a little bit more enrichment and understand, especially if you're not quite sure you understand effective nuclear charge and those terms that we talked about, because they are kind of a weird term to try to understand and a concept to try to grasp. So at this time you need to work on your POGIL on Coulombic attraction and do the puzzles 1 and 2. And if you need video help for either of those, you can see those slides, those spots in your assignments and get help with those.